So welcome everyone to day 10 of 2 questions of physics per day series. So here we have first question which says that calculate the probability that the speed of an oxygen molecule will lie in between 100 meter per second to 101 meter per second at 200 Kelvin temperature. The mass of an oxygen molecule is about is a 32 atomic mass unit, and you have to take the Boltzmann constant as 1.38 multiplied by 10 to the power minus 23 joule per Kelvin, and the Avogadro number is as usual the simplified version, which is 6 multiplied by 10 to the power 26 kilo per mole. Okay, so you know that how the question might be playing with you. Sometimes they will use the per mole, okay, sometimes they will be using the kilo per mole. So if you don't focus on the given quantities, you might make the mistake, okay, that you will use the or you might get confused as well. So you should always know your basics correct, that Avogadro number has only one form, which is 6.022 multiplied with 10 to the power minus 23. It is simply that the one dozen banana is always 12, whatever. Okay, one dozen, whatever, one dozen, whatever is 12, whatever. Okay, so here we are being asked to calculate the probability that the speed of an oxygen molecule will lie in between 100 to 101 meter per second. The temperature is 200 Kelvin because it will differ. You know that Maxwellian distribution will differ if you change the temperature. So at 200 Kelvin, this has to be 100 per meter second and 101 per meter second. So the speed will always in between this limit. Now we know that the probability distribution of the molecular speed is given by the Maxwell-Boltzmann distribution, and we will see what this distribution looks like. The mass of an oxygen molecule is calculated using the molar mass and Avogadro number. You know it, okay? That if this, you should always know that if it is given as 32 U, there is mass of one atom, mass of one atom or molecule. In this case, it is oxygen, so it is going to be molecule. But if it is 32 gram, then you should know that it is mass of 1 mole molecule, 1 mole molecule. So 1 mole is always, you know that it is Avogadro number. Okay, now we should always know that what is this speed distribution function. This is the speed distribution function which is given by Maxwell-Boltzmann statistics, which you are also will be also studying in the statistical mechanics within the thermal physics realm. Now you have some given value that you have the molar mass of the oxygen to be this much in the kilogram. Okay, in the atomic mass unit it is 32, but in the kilogram it is this, which is derived by using the division of the Avogadro number. Division with the Avogadro number, you have the Boltzmann constant, this temperature 200 Kelvin, and the velocity which is 100 meter per second, and the change in velocity is around 1 meter per second. So we know that this distribution function has to take the value this if you have to find that range. Okay, this is the way the distribution function works, that you have the range of the number. Okay, and you have the distribution function and you have the range of the velocity. So within this range of the velocity, around when velocity is 100 meter per second, you will get this much number of molecule. So out of those number of molecules, only this number of molecule will be available within 100 and 101 meter per second. This is the way distribution function explains the concept to you. So now you know that this is the value. You should repeat with me that distribution function f as a function of v is 4 pi multiplied by m divided by 2 pi kt whole power 3 by 2 v square, then there comes the exponential term and minus half mv square divided by kt. This is what you need to remember, and you also need to remember how does this work. So now you need some calculation only, just simplify it numerically to get the distribution function around this value. Okay, so the probability that it lies is around this, and now let us move forward to the next question. So now let us solve the next question, that you need to prove that for a Maxwellian gas, you need to show that the average speed multiplied by the inverse uh, average of the inverse of the speed is going to be 4 divided by 5. Okay, so this is, let me call you, this is average speed, this is average of inverse of speed. Okay, so what we can do, we can use the definition of the average. So definition of the average will be like, if we need to find the definition of average of function f, then it is going to be 1 by total number from 0 to infinity divided by the function multiplied by the number. Okay, so we are going to use this here, and using the Maxwell Boltzmann distribution, we can write that dnb is equal to 4 pi n multiplied by m divided by 2 pi kt whole power 3 by 2, as we did earlier, and v square exponential minus mb square divided by 2 kt dv. So in that way you can calculate the average to be around this value. Now you are required to evaluate this particular integration. Okay, so it will be done by using the substitution, where we are going to call the constant m divided by 2 kt as a. So this will be the form of the integration which you are going to have, and it is a standard well-known integration of this form. It is a standard well-known integration of this form which you always remember. So it is integration of this particular function x exponential minus x square dx from 0 to infinity, which is going to be 1 by 2a. Okay, in that way we have the value of a, and when you substitute, you are going to get the value of the integration to be k t by m. Okay, so in that way the final expression for the average of the inverse of the speed is going to be this. Okay, and now we have done nothing more than the simplification, and the only the main formula was this. Okay, that we were using the definition of the average of any function. Okay, the main formula was, we use that definition of average. And we know that the for Maxwellian gas, the average speed is given by 8 kt by pi m, and this 8 by pi turns into 2.55. This is what we were using the in the previous problem as well. So it is 2.55 RT by molar mass, or you can use 2.55 kT by small m, that is mass of the one molecule only. So molar mass and molecular mass, they are different. Molar mass means the mass of anything which has Avogadro number of the content. So when you multiply them, you are going to get the value which is 4 by pi, hence proved the statement of the question.